In this video, we will discuss about Poisson's equation, Laplace equation and its applications. And this Poisson's equation and Laplace equation, they are related to electrostatic field. And here we can have electric field E, and we can relate this thing with potential V, and that is relation is E equals to minus gradient of V, where this is the gradient notation and this V is a scalar field x, y, z. It could be a function of x, y, z in rectangular coordinate system, in cylindrical rho, phi, z, and in spherical it will be r, theta and phi. Okay, but this is a scalar field. Okay, this is a potential, whereas E is a vector quantity, x, y, z, it's a vector field. And they are related by this thing. So if you take gradient of a scalar field, we are getting one vector field, and that is E equals to minus grad of V. Okay, this is first, and another one is Gauss law. We can use the Gauss law, and it says that the total surface integral E dot ds, this thing we have discussed in detailed way, closed surface integral of E dot ds is total charge enclosed upon epsilon naught. And now this charge enclosed, that we can consider as rho into dV. Rho is the volume charge density. So if I integrate over volume, then we will get total charge enclosed and upon epsilon naught. And this one, left hand side, this E dot ds, the surface integral, we can convert it to volume integral using divergence theorem. So using divergence theorem, if I convert it to volume integral, then over volume V, it will be del dot E, the divergence of E and dV. This one, so this side it is, I can write rho upon epsilon naught dV over volume V. Now if I compare these two, then what we will get? Del dot E equals to rho upon epsilon naught. So this is the differential form of Gauss law. Now we can use these two, we can combine these two to get another relation. So these two, if I relate, so you can see that we have got already del dot E equals to rho upon epsilon naught, and we have got electric field is minus of gradient of V. Now if I replace this E here, okay, what I'll get? Del dot, this is your minus grad V, and that is equals to rho upon epsilon naught. So this minus sign I can take this side, and this del dot grad, this is notation we will use Laplacian operator del square V, that will be equals to this minus sign, I will put it here, minus rho upon epsilon naught. And this equation is called Poisson's equation. And when there is no charge for charge free region, if rho equals to 0, in that case this del square V we can write as, this is 0 only. So this is for charge free region or source free region. This is called charge free or source free region. And this equation is called as Laplace equation. Most of times we'll find that Laplace equation is applicable because maximum region is charge free. Only certain regions charges are there, charge distribution is there, and rest of the space are charge free. And whenever we'll find the charge free region, there we can apply a Laplace equation, we can solve for that. So this Laplace equation is most important. I'll be discussing some results of Laplace equations where you can apply. Okay, now before that, this del square V equals to 0. In the rectangular coordinate system, this is written as del square V del x square plus del square V del y square plus del square V del z square. And this three term addition is becoming 0. So this is the Laplace equation, and we can use this Laplace equation to find the potential in a region where there is no charge. Okay, I'll take few examples. One example I'll take for this rectangular coordinate system, and others two. One I'll take from cylindrical, and other I'll take from one concentric spheres. So three examples I'll be taking. Sorry. Now first example. It's about two parallel plates. Okay, like this. I have three coordinate systems. This one, rectangular coordinate systems I'll consider. This is x, this side is y, and this side is z. And I'll consider one plate, and this plate is at here, and at the xy plane, another plate is at, I'll consider in different one, here. So this plate, this is one plate, this is at z equals to, suppose A, okay. So this, or D, suppose this gap is D, this gap is D. Okay, now the lower plate I'll construct. So this is the y-axis, and the lower plate is becoming like this. I can have this plate. So this blue one is another plate. This plate, it's an infinite plate. Right now I am considering it's an infinite plate in xy plane. So only the difference is, the vertical difference is d. Okay, the vertical difference is d only. Sorry. And this potential, its potential I am considering it's a V naught, and its potential is suppose V1, right? So what is in between these two plates? This region is totally charge free. I can apply certain charge plus q here. Okay, I can apply plus charge q here and minus q charge here. But in between these two plates, there is no charge at all. So this is your free space. So this in between region is totally free space. So I can say this is your free space or charge free region, right? And there we can apply the Laplace equation. So Laplace equation, the del square V equals to 0. Now this term is having three terms as I discussed. Del square V, del y square, and del square V del z square, and that is equals to 0. Now as these two plates are infinite plane and it is on xy plane, parallel to xy plane, so I can assume that this V potential at any point, suppose here or here or here, anywhere in between this one, it's symmetrical or it's independent of x and y. It could be a function of only z. Okay, so V is not a function of x and y, meaning is that del square V del x square, that is 0, because it is infinite along x directions. It has no variation along x. Okay, so V is not having any variation along x. That's how its derivative is 0. Double derivative is also 0. Similarly, double derivative of V with respect to y, that is also 0, because along y it is infinite. So V is not a function of y. Thus derivative of V with respect to y is 0 and double derivative is also 0. So these are the two things we have got, because it's an infinite plane on xy plane parallel to xy plane, right? So this part, so can you see from here, so this is becoming 0, this is becoming 0. So forcefully this part it's need to be 0. So del square V del z square, it has to be 0. Okay, so what is the equation? Del square V del z square, it has to be 0. So already I said that V is not a function of x or y, so it could be a function of z only. So there is no meaning to carry this thing, because V is a function of z only. So I will put normal double derivative d square V dz square, and that is equals to 0, because it is function of only z. There is no need to consider partial derivative right now, because V is only function of z and we are taking derivative with respect to z, right? Now what is the solution of this one? So first this thing I can write d dz of dv dz, that is equals to 0. So derivative of something is 0, so obviously this part should be a constant. So dv dz, it should be a constant, and that is suppose k1. Okay, now what is now V? Now dv I can write this k1 into dz. Now if I integrate on both sides, what I will get? This is V, that is function of z, equals to k1z plus k2, another constant. So this is the expression, right? Now we can apply boundary conditions. The lower plate, can you see? This lower plate is having potential V0, and upper plate, that is separated by d distance, it is having a potential V1. So what you can write? We can say that at lower plate means z equals to 0, V equals to V0. So if I use these things, then what I will get? So I replace V of z equals to V0, and I'll put z equals to 0 here. So this is 0 plus k2, that imply k2 equals to V0. Again next, at z equals to d, at that point the potential above plate, top plate, that potential is having V equal to V1. So what I can write? So I replace V by V1, and that is equals to K1, and this Z is replaced by D, and this K2 is already I have got V0, right? So from here I can express K1. What is K1? It's nothing but V1 minus V0 by D. Is it okay? So this is the expression for K1 and K2. We have got it. So what is the final expression for this? B of Z, function of Z only. This K1 I have got these things, B1 minus B0 by D. Okay. This is K1 into Z plus K2. K2 is nothing but V0. So once we have got the electric field, this potential distribution, then we can find out electric field. So electric field E is nothing but minus grad V. And what is the gradient? Gradient, this is nothing but minus actually del V del X, X vector, del V del Y, Y vector, and del V del Z, Z vector. Okay. Now here you can see that V is not a function of X, not a function of Y. So this part is becoming 0. So this is becoming 0. This is becoming 0. Only it is having along Z directions. Okay. And what is the del V del Z? So this thing I can write then minus dV dz along Z vector. So this is a V of Z. If I take derivative, this is constant part. And so this derivative of Z is 1. So this constant K1 will remain same. So this is minus V1 minus V0 upon D, and its value is, its derivative is 1. It is along Z direction. Okay. So electric field is this directions. Okay. And this one I can write as V0 minus V1 by D along Z directions. I am assuming that V0 is more than V1. If it is true, then this is positive Z directions. So we can show in this figure, if V0 is more than V1, in that case the electric field direction will be along Z directions, and we can show it like that. Okay, I can take different colors. So these are the field, electric field. Here and here it is like this, here it is like this. So everywhere the field is along the Z axis. Okay, and the magnitude is this potential gap V0 minus V1 upon D. And for this flat plate, in the previous lecture, using Gauss law, we have got the electric field within the space. Okay, so can you see this one? If I have these two plates, this one plate, and if I have another plate here like that, like this. So in between, so this is the charge density sigma, and this is your minus sigma. Then electric field will be only from this plate to this side, and outside there is no electric field. In between only the electric field, and this electric field magnitude we have computed as sigma upon epsilon naught. So in the last video we have discussed this thing, you will get the link. Okay, so they are using the Gauss law. We have got the electric field between two plates. One plate is having charge density sigma, other is minus sigma. In that time it is having sigma upon epsilon naught. Okay, so this magnitude and this magnitude now we can compare. Okay, now if I compare these two, so what I'll get, I can simply write this V naught minus V1 by d, this is the magnitude of electric field, and that is same as sigma upon epsilon naught. And what is sigma? If total charge is Q and total area is A, then sigma is nothing but the charge per area, okay, upon epsilon naught. Now here we can define the capacitance between these two plates. So these two capacitors, this is, I'll apply, this is minus charge Q, here it is a plus charge Q. So one plate is having plus charge Q, other one is minus Q charge, and they are separated by a gap D. The capacitance C we can define by, it's a Q upon voltage difference V0 minus V1. So Q upon V0 by V1, that you can easily write that A into epsilon naught upon D. So this is the expression for two parallel plate capacitors. That's A is the area of the plates, epsilon naught is the media constant, and D is the separation gap between these two. Okay, I hope you have got this idea. This is the capacitor for this one, right? Now next we will consider cylindrical and spherical, and before going to that we need to understand the Laplace equations del square V equals to 0 in cylindrical coordinate system and spherical coordinate system, how it look like. So for that we'll consider one thing. So if any coordinate system, the elemental length dl vector is written in this form, that is h1 is one constant and du1 u1 vector, it's one direction vector is u1 vector, its elemental change is du1. Okay, similarly h2 du2 u2 vector, unit vectors, and h3 du3 and u3 vectors. So u1 u2 u3, these are three unit vectors in certain coordinate system. Okay. If it is so, then the Laplacian operator, the del square V, that is a function of u1, u2 and u3. Okay, that could be written as 1 upon h1, h2, h3 times, be careful here, it is a del u1, and inside that I will consider h2, h3 upon h1, that corresponding 1, it is divided by h1, times del v del u1. This is the one term. And second term, very similarly, del u2. So here is the u2, so this is h2, and this one will be h1, h3. And it is del v del u2. Okay, and last one is del u3. So obviously it will be h3, and one is h1, h2, this product, and it is del v del u3. Now we can relate this thing to cylindrical and spherical coordinate system. In cylindrical coordinate system, what is cylindrical coordinate system? We have, so with respect to x, y, z, any point we can locate as on cylinder of this one. Okay. So this could be one cylinder. Its radius from the center point is rho, and this point will make this vertical plane will make an angle phi with x-axis, and vertical height, this height is z. So this point is rho, phi and z. And in this coordinate system, dl vector is defined as the change in rho is d rho rho vector. But if there is a change in phi, d phi, corresponding length change is rho times d phi and phi vector, unit vector, and along z is simply dz, z vector. So if you compare, its coefficient is 1 is multiplied, its rho is multiplied, it is again 1 is multiplied. So h1 in this case 1, h2 is rho, and h3 is again 1. So what is del square V? So that you can rewrite as, so 1 upon h1, h2, h3 is nothing but 1 upon rho, 1 into rho into 1, okay, multiplied by. So first term, del by del rho. Then what is this? Numerator is h1 is 1, and h2 is rho, and h3 is 1. Then del v del rho. Okay? Plus, next one is del with respect to phi, del phi. And this time, denominator is rho. And numerator, these two product 1 and 1, h1, h3. And it is del v del phi. And last one is del z, and this time this coefficient is h3 is 1, this is rho into 1, and it is del v del z. Okay. Now we can simplify it a little bit. So this rho I can take outside because it is a function of rho. So first term is becoming 1 upon rho del rho and rho times del v del rho. Next one, here this rho I can take outside because it is derivative with respect to phi. So this rho if I take outside, so this rho into this rho is 1 upon rho square. And now I can take a double derivative, del square v with respect to phi square. And last one, this rho I can take outside, and this rho is there. So these two will cancel out. So I will be getting only del square v del z square. So this is for cylindrical coordinate system. Similarly, you will be getting for spherical coordinate system. So let us discuss this thing first. So it's for spherical coordinate system. Remember, in spherical coordinate system, we will consider the position vector. Okay, this is x, this is y, and this is z. We will consider one sphere kind of thing. Okay, and here also I will consider one sphere. So point could be here. This is one point P. It is on surface of a sphere whose radius from origin, this radius is r, and the angle with vertical z-axis is theta, and with horizontal xz plane, so this plane is making an angle phi here. So the coordinate is r, theta and phi. So this thing I will discuss in detail in one video. Okay, how to get all those things. So here elemental length vector is defined as, so if there is a small change in r, so it is a dr r vector, that's simple. And change in theta, this is r d theta theta vector. And for corresponding change in phi, it will be r sine theta d phi phi vector. So here you can note that, so here nothing is multiplied, h1 is 1, so h1 equals to 1, but here h2 equals to r, and here h3 equals to r sine theta. Okay, so how to represent this Laplacian operator? So you can see that this now del square v I can write as 1 upon h1 h2 h3. So this is 1 into r sine theta. Okay, this is multiplied. Then del by del r. Then h2 h3. So this is r into r sine theta. It's r square sine theta upon 1 into that del v del r. Okay, plus next term is with respect to theta. So del theta. Now in this case h1 h2 by h1 h3 by h2. So 1 into r sine theta. So it is r sine theta by h2 is r. So r will cancel out into del v del theta. Okay, and last one with respect to phi, del phi. Now what is the factor here? So h1 h2 upon h3. So 1 into r numerator, and this is your r sine theta. Okay, and it is multiplied by del v del phi. Now we can simplify it a little bit. So what is the first term? Now in the first term you can see that this r square I cannot take outside because it's a derivative with respect to r. So this sine theta I can take outside, no problem, because it's independent of theta. So this sine theta will cancel out. So what's the first term? It's 1 upon r square. It's a del r, and within that sine theta I have taken outside and it cancel out. So it is r square del v del r. Okay, then plus sine. Now here this sine theta I cannot take outside because it's a function of theta. So it is 1 upon r square sine theta. Okay, and this is del theta of sine theta del v del theta. Okay, and last one, this r cancel out. This sine theta I can take outside. So it is again 1 upon r square sine theta, r squared sine squared theta, because sine theta and sine theta will become sine squared theta, and it is simply, there is no terms here, scaling factor, so I can write del square b del phi square. So this is the Laplacian operator for spherical coordinate system. Now we will take up two problems. One is cylindrical coordinate system, other one is spherical coordinate system, and we will use Laplacian operator, Laplace equation to solve this one. So next example number 2. We have two cylinders, concentric cylinders, that we can consider. Suppose I will consider in this way. This is rectangular coordinate system, this is x, this is y, and this is z, but we will consider cylinders. One cylinder is like this, okay, and this is the cylinder, and it's a long cylinder. Okay, another cylinder I'll consider, that is a larger, okay, and this one. Right, and these two cylinders, they are having their, from this axis Z, the radius is rho 0, and this radius we are considering it is a rho 1, and the potential on this surface, the green one, this here potential is V0, and for this one the potential is V1. Okay, now we wish to find out, this will form a capacitor again. So what the capacitance in between these two cylinders in this space, what is the potential distribution, that we will try to find out. Okay, so it within the space where I'll consider one point rho. So any point rho, I can consider point 1 here, that is the distance rho. So that rho is within rho 1 and rho 0. So this region we will consider between two cylinders. So there, what are the Laplace equations? So Laplace equation is equals to 0. Now as it is symmetrical, it will vary with respect to rho only. It will not vary about z and phi, because it is symmetrical with respect to phi and z. So this variation with respect to del phi of v, that is equals to 0, and del v del z, that is also 0. So these two things we will consider. So only the first term we will be getting. In the Laplace equation, the first term, can you see these things? In the Laplace equation, this is the first term, 1 upon rho del rho, rho into del v del rho. This term is there, and this term is already 0. This is also 0 because of symmetry. Then this has to be 0. Right? So once this is 0, this is 0 because of symmetry. So this has to be 0, but it implies that, so what is this? 1 upon rho times del rho, rho times del v del rho. This is the term, and that has to be 0, but it does not imply v is independent on rho. That v is depending on rho. Still it is 0. So what are the first things? So these things rho I can multiply, it will remain 0. So del by del rho, rho times del v del rho, that is equals to 0. So this inner one should be constant, then only derivative is 0. So it's imply that this rho into, I can write dv d rho, because v is only function of rho. There is no meaning to take a partial derivative. So rho into dv d rho, and that should be a constant, and that I will consider k1. Next, what I will do? Del v del rho will be equals to this k1 upon rho. Then what I will do? This dv I can express this k1 upon rho and d rho, and now I can take integration on both sides. So what we will get? So this integration is v, this is your k1, and 1 upon rho d rho is the ln log rho base e, we will consider, plus another constant k2. So this is the form of V is a function of rho. Now we can put the initial conditions. You can see that at when rho equals to rho 0, that time V equal to V0, and when rho equal to rho 1, the potential is V1, right? So can I write these two? At rho equal to rho 1, rho 0 suppose, then V equals to V0, and second one is at rho equals to rho 1, V equals to V1. So what are the equations? So this was the equation. There we can rewrite. Okay, so V equals to, so in this case we can write this V0 equals to K1 ln rho 0 plus K2. Similarly here it is V1 equals to K1 times ln rho 1 plus K2. So if I subtract these two, our objective is to find the gap. So V0 minus V1, what I will get? So this is K1 common, it is ln rho 0 minus ln rho 1. Okay, and this thing I can take the minus sign common a little bit, K1, then ln rho 1 by minus ln rho 0, and that we can combine ln rho 1 upon rho 0. Because rho 1 is more than rho 0, that's how I want to take this form, rho 1 upon rho 0. Okay, nothing else. Fine. So this is the voltage difference that we have related these things. Okay. So what is the K1 right now? So K1 is nothing but minus V0 minus V1 upon ln rho 1 upon rho 0. So what is the expression for V? So V is a function of rho, and that we have got K1 into L. So K1 is this thing, minus V0 minus V1, this is ln rho 1 upon rho 0, this is K1 times ln rho plus K2. K2 we have not found, so we can find out K2. Okay, but we are not interested to find exactly for K2 because it is not required. So why? Because electric field is nothing but minus of gradient of V. So as this is a minus of gradient and it is varying with respect to rho only, so I can write minus dV d rho. That's all. And V we have got. So if I take derivative, this part will become 0. This constant 0. So what is happening? So this one. So can I write this one? It's a minus sign. And dV d rho, if I take derivative, its value will be 1 upon rho. And this is minus sign. So minus, again V0 minus V1 upon this ln rho 1 upon rho 0, and this is 1 upon rho. And this is about rho vector. This is the electric field. Now for these concentric cylinders, if I have a charge Q, so inner plate or inner cylinder is having a charge Q and outer one is minus Q, then we can use Gauss law to find the electric field within these two cylinders. That thing we have done already in the last video. So how to apply Gauss law to find electric field? So what we have done there, so we have considered say at this place we have considered this cylinder again, like this, with radius rho. So within that, how much charge is there? So E dot ds equals to total charge enclosed by this one. So what is the E dot ds? So that also we can consider right now. E dot ds, total charge, and total charge will be in this case. So if I consider the charge density, line charge density rho L, okay, and this length is capital L. So rho L is the charge density. So rho L times L, that will be the total charge inside these things. Okay, can you note this thing? It is nothing but total charge enclosed upon epsilon naught, and this thing we are getting rho L times L upon epsilon naught. And what is this one left side? E is constant everywhere. So here everywhere electric field is perpendicular, okay, and so E is constant. And what is surface area? This surface area, so 2 pi r into L. So curved surface area for this cylinder is 2 pi r into L. So it is E times 2 pi r, means here rho, and it is L. Is it okay? And that is equals to this thing, rho L into L upon epsilon naught. So this L cancel out. So what is the electric field magnitude? That is your rho L upon 2 pi rho epsilon naught. Now we can equate these two. So electric field, so this is the magnitude. Can you see this thing? So this is the magnitude part, and this is direction only. So now I can equate these two. So what you will get if I equate these two? So this is rho L upon 2 pi rho epsilon naught, and that is same as, so minus 1 is plus, it's a V naught minus V1. This is ln rho 1 upon rho naught, and it is rho. And this rho will cancel out. Okay, be careful, this is rho L, nothing with this radius, it's a charge per length. Okay, so now this thing I can write as per length wise. So total charge is Q and total length is L. So small L I am considering total length. So this is 2 pi epsilon naught, and that is equals to, this is the voltage gap, it's a V. V is the voltage gap, V naught minus V, and it is a ln rho 1 upon rho 0. So capacitance C is defined by this Q by V. So this Q by V, if I consider, so this is becoming 2 pi L epsilon naught upon ln rho 1 upon rho 0. So this is the expression for concentric cylinders, their capacitance. Okay, I think you have got this point. And last example we will consider, and that is the concentric sphere. So last example we are considering the concentric sphere. So we have two spheres. So quickly we will do these things. So this is your x, it's y, it is z. I have two spheres. One sphere is like this. Another sphere is this one. Okay, and the potential here, it is suppose V1 and this potential and this charge is suppose minus q, and I can apply V naught potential here, and charge is suppose plus q. Now in between these two, if I consider any one point here, and this point, the radius, suppose the inner one radius is R1, so I also consider the radius, this is R1, and this radius is R2, and any point with distance from center is R. So here R is within R2 and R1, that region we are considering. There again we can apply the Laplace equation, del square V equals to 0, but it is cylindrical coordinate system. So here also again we can apply del square V equals to 0. So in cylindrical coordinate systems, what you will get? 1 upon r square del r square. Hello. Video okay, so this is 1 upon r square del V del r, and that is equals to 0. So basically this constant should be, this is a constant, r square del V del r equals to one constant k1. So what you will get? dv equals to k1 upon r square into dr. So if I integrate both sides, what I will get? The v expression for is minus k1 by r plus k2. Is it okay? Now you can put the potentials, boundary conditions here, with r equals to r1, potential is v naught. So these things you can do it by yourself. So I can write v naught equals to minus k1 by r1 plus k2, and v1 equals to minus k1 by r2 plus k2. So from here you can find the k1 value. Just subtract these two, v0 minus v1. So can you do that? So v0 minus v1, what you have got? This is minus sign, I can consider, take common, minus k1. So it is a minus k1, 1 upon r1 minus 1 upon r2. Okay. So this is the expressions. So k1 easily I can express that v0 minus v1 upon, it's a minus sign, 1 upon r1 minus 1 upon r2. That's okay. So what is the electric field? Electric field is minus of grad v, and where v we have got, that is your minus k1 up by r plus k2. So if I take derivative of this one, what I will get? Its second derivative of this one is minus plus 1 upon r square. So it remain minus k1 by r square. And where k1 is these things. And for this concentric sphere, if you take a Gaussian surface at this place, the electric field, the expression for electric field will be q upon 4 pi epsilon naught r square. That thing also we have defined. Using Gauss law we have got it. So please follow the previous video. Now these two we can compare. So these things we can compare with. So electric field we have got, magnitude we have got q upon 4 pi epsilon naught r square, and this is same as this is k1, and this is, so this minus sign cancelling out, is v0 minus v1 upon 1 by r1 minus 1 upon r2 by r square. So this r square will cancel out. So what is the capacitance C? C equals to q by v. V means here v0 minus v1. So this is 4 pi epsilon naught upon 1 by r1 minus 1 by r2. So this is the expression for the capacitance for two concentric spheres. I think you have got this one. Okay, so if you have enjoyed this video, you can press the like button. I will be discussing more video in this channel. Keep watching. Thank you.